Hello, today I'll be introducing a new series which is Materials Engineering for Semiconductor Devices. So, before I start, maybe I should first explain what this series will be about. So, this series will be about explaining semiconductor engineering from the perspectives of materials engineering, or more broadly speaking, material science and engineering. So, what this series will briefly cover would be firstly semiconductor materials, very briefly, followed by in more in-depth would be the microfabrication processes and technology for integrated circuits. And the third thing that we'll cover would be materials characterization methods that are commonly applied to analyze semiconductor devices. Okay, maybe I'll introduce myself. I've just recently finished my degree in material science and engineering in NUS, and I'm waiting for official conferment of the degree scope. And I'm personally interested in semiconductor technology and fabrication. So what I want to do here is to provide an introductory yet sufficiently comprehensive series on what I've learned in school that I found extremely useful in my experience in industry, and also about reading more about the semiconductor industry. And so I intend to conduct this series from the perspective of a student. So basically telling you what matters in an accessible way as much as possible. And so what you can look forward to, in other words, how I plan to structure this series would be to first conduct a non-technical summary at the start of each video. Because I acknowledge that not everyone needs to know the hard science behind everything. Because for example, let's say you are someone who's going to work, maybe you're a computer science person who's going to work on software automation for a semiconductor fabrication company. You do not need to know, right, how each process works, but you still need to know roughly how the fab operates, for example. Or let's say you may even be someone who's just interested in the industry, maybe someone who wants to buy the stocks of semiconductor companies, right? You don't need to know how the science behind the processes work, but you need to know roughly what actually happens in this industry, which is fundamentally still a manufacturing industry. And so, following the non-technical summary at the start of each video, I'll then go into information about techniques and processes, or more specifically, information that is essential to understanding the content, because I plan to avoid most of the daunting mathematical and physical derivations. So there will not be that many equations except when it is absolutely necessary or important to take note, especially like let's say for future understanding. And I plan to cover mostly the most industrially relevant points, yet being sufficiently comprehensive that you can use the knowledge that you learned in this series to explore more on your own. So without further ado, maybe I shall start on the first chapter, which is the introduction to semiconductors, possibly the most fundamental chapter or episode of this series. So once again, this will be the overview of what I'll be covering in this chapter, so it's pretty long, so bear with me. So firstly, a non-technical summary. So what are semiconductors? You can think of electrical conductors as the highway where there's a lot of cars that travel, and the cars travel at high speed, high volume. There's like no traffic lights or anything, no barriers to the flow of cars at all. And you can think of electrical insulators as a closed road, right? So the road is blocked, is closed, right? You're not allowed, you're not able to drive on it. No cars are able to drive on it at all. So zero, right? And what about semiconductors? Maybe semiconductors can be thought of, let's say, a road where there is a traffic warden directing traffic. So depending on the traffic warden, who is presumably following a set of traffic rules, he will direct the traffic, right? Sometimes in one direction, sometimes in the other direction, sometimes stopping the traffic altogether, right? And sometimes regulating the speed or the flow at which the traffic flows. And so this is the idea of semiconductors, right? So semiconductors are not like conductors that electrons, or basically cars, right, in our analogy, can flow unhindered. Nor is it like insulators where there's completely no flow of electrons, right, like a roadblock, right, no flow of cars at all, right. But instead, it allows current or electrons to flow through to a certain extent, and also what extent this is can be modified by what we call dopants. So for example, your nitrogen, your phosphorus, your arsenic, these are elements that can be added into silicon to modify the way it transports electrons. So it's kind of like the traffic warden in our analogy. They help to direct the flow of cars in this way, in that way, or stopping the flow or allowing a greater flow, right? Nitrogen, phosphorus, and arsenic and similar atoms like that, which we call dopants, are what controls the flow in semiconductors. Or maybe you can say it modifies the flow in semiconductors. And so because of the interesting electronic properties, rather the way they transport current, uh, semiconductors have found a lot of use, right, in integrated circuits. So what we know as computer chips, right, your CPU, GPU, you may have heard of it, especially if you're into gaming. Also things like solar panels, right, renewable energy source, very important renewable energy source, as well as light emitting diodes, LEDs. Okay, so that's the end of my non-technical summary. Let's go into the more technical content. Alright, so let me first cover what is basic band theory. So consider, let's say, a material is like a building. So, and the electrons are like people that fill up each room in the building. So let's say it's like a hotel, so one person per room, right? One electron per energy level in the material. And so let's say that um, every floor, right, you have people that are occupied. You have rooms that can be occupied. So you fill up each room with people. So you fill up each energy state with electrons. Up there, right, you fill it up completely. So this is like the case of, like, let's say a conductor, right? We'll see why later. And let's say the floor which is fully filled, above which there's is all empty. We shall call that, let's say, the Fermi level, right? The Fermi level. So it is a level that kind of by definition, anything above it, any rooms above it is empty, and all rooms below it are filled, right? At ground state, okay, which is at like a ground state level, okay. And so however, consider the case where you have an interesting building like this one in Singapore over here, where we have like a blank, right, a place where there's no rooms, right? It's just an empty space, right? Maybe it's a garden or whatever, but we don't care, there's no rooms, right? So we can so if the Fermi level is right in between, right, this space, so we have the floors below, the rooms in the floors below, all occupied by people, right? All occupied by people. So all occupied by electrons. However, right, the rooms above this gap, right, is empty because the Fermi level, right, is between, right, the top segment and the bottom segment. And so what we want to do is, let's say we want to access the higher floors from, let's say, an occupied floor, right, on the lower segment. You want to access the higher segment. You can imagine you have to climb a lot of stairs, right? Correct? Because there's this large gap, right? It's not simply one floor above. It's like maybe, let's say, looking at this photo, it looks easily 3 or 4, right, levels above. So you do need to climb a lot of stairs. So that takes energy, right? You feel tired after that. Okay. So this is like the analogy of basic band theory of materials. So let's take a look at, the actual band theory, the band diagrams of materials. So we see here in the insulator is very similar to this interesting building we see over here. And so in the insulator, we have basically your valence band. So your valence band is the one that is actually occupied, filled with electrons, and your conduction band is empty. And so in your valence band, the electrons cannot move. They are fixed in position. Why? Because there's no space around it to move. You cannot move up, right, to empty space to move left or right. You cannot, because in the band gap, in what we call the band gap, is devoid of spaces for electrons to move, right? So it's like just now the building here, no rooms, right? You cannot be dangling in mid-air, right? Correct. So same thing here. The electrons cannot exist in any area in this area, right? So to move, it has to go up to the conduction band. And when I mean up, I mean higher up in energy, because the y-axis over here, right, the vertical axis is electron energy increasing upwards. Okay, and so if you want to go to the conduction band where you can conduct, right, you can move, the electrons can move freely, right, it requires to overcome this energy, right? Can you imagine walking up 4 flights of stairs, consume a lot of energy, right? So same thing here, electrons consume a lot of energy to go up. Okay, so so effectively that is why insulators don't conduct electricity, because electrons simply do not have the energy under normal conditions like room temperature and all that to go up to the conduction band to move around. So electrons stay put, and as you learned already in secondary school, right, conduction of electricity in materials arise from electrons, right? Most materials arise from electrons. So electrons can't move, so it's not conductive of electricity. Okay? And how about metal, right? Metal, you see an interesting case of an overlap between the conduction band and the valence band. So that means for electrons to enter into the conduction band to move around, right, it requires zero energy, very little or even zero energy. If it overlaps, it does not require any increase in energy to enter into the conduction band. So you can imagine that at room temperature, many electrons will jump to the conduction band and move, right, be free to move. And when you have electrons free to move, what do you have? You have free mobile charge carriers which can help to conduct electricity, as all of you have learned in secondary school. Then we have the interesting case over here of the semiconductor. So the band gap, right, the gap in which there's no available electron energy states still exists in the semiconductor material, right? However, it's much smaller than that of the insulator. So what this means is that if, let's say, you apply a bit of heat or maybe a bit of other forms of energy, light, for example, right, you can maybe excite or encourage some of these electrons in the valence band to move up to the conduction band and conduct electricity, right? So basically, this is a semiconductor, right? It's not really like a metal, a full conductor of electricity. However, it is also not like an insulator. It can conduct electricity if the conditions are right. Okay, so let's take a look at an example, a classic example of a semiconductor, which is silicon. So silicon has this structure over here, right? So we have 4 covalent bonds, right, formed by each silicon atoms with the neighboring silicon atom. So actually, it's actually a tetrahedral geometry, right? But for the sake of drawing it in a 2D diagram, right, they just draw it like this. So let's just treat this as an illustration. So we see that the electrons are localized in the silicon-silicon bonds. They are fixed there, right? You do not see the case like in a metal where there's a sea of delocalized electrons free to move. No. The electrons are fixed in the silicon-silicon bonds, right? So yeah, unfortunately they can't move, and that is the reason why silicon, right, has a band gap, right? Normally, right, if the electrons are not excited, they can't move, right? They are stuck in the valence band, they cannot move. However, this can change, right? How can this change? This can change by adding certain atoms of other elements, right, into the silicon. So let's say we add boron. Boron, if you know, you can just refer to the periodic table. Has 3 valence electrons, which is 1 less than silicon. So if we can make boron replace the silicon, or what we term in material science as like occupying a substitutional site, right? If we can make it occupy a substitutional site, right, we realize that there's a vacancy of electron, right? One of the bonds here, the BSI bond, is only a 1 electron bond, right? There's an absence of an electron that should be there if it was silicon, right? So we can call this absence of electron a hole, right? We call this a hole. So you can think of it as like a bubble in water, right? A bubble in water. It's the absence of water in the bubble, right? So it's a hole. So likewise, we use the same terminology. Okay. Then we can also consider, let's say, putting antimony, right, into silicon. So once again, the substitutional side. So it has 5 valence electrons, right? 5 valence electrons. So after forming the 4 covalent bonds, it has 1 electron left, right? So where does this electron go? We can think of this electron as being released somewhat from the antimony atom, right? And so in a sense, because it is not localized, it's not fixed in a covalent bond, it is free to move. So whereas in the case of boron, we have an absence of an electron. In the case of antimony, we have an excess electron. So for the case of antimony, it's very obvious to see how this excess electron can conduct electricity, right? It will be free to move, right? It's free to move. So you apply electric field, the electron moves. And when the electron moves, right, it's able to conduct electricity. So how about the case for boron? So for the case of boron, it's more interesting. So an electron can move to occupy the hole, and the hole moves, right? And another electron nearby moves to occupy the hole, and the hole moves again, right? So in the sense, the movement of holes is the inverse of the movement of electrons, okay? However, because although it is electrons that are actually doing the moving, because electrons are the real particles here, for the sake of convenience, you normally call it as a hole moving. A hole moves. So if you have a hole, which is a positively charged entity, right, you can think of it as a positively charged entity because the absence of a negatively charged electron, right? So you have a freely moving or free mobile positive charge, and so that is also a charge carrier that can conduct electricity. Okay, so how do we visualize this in the Venn diagram? So for the N type, right, basically the introduction of antimony introduces electron energy levels very near the conduction band. So with just a bit of heat, a bit of energy, normally heat is enough, like room temperature enough, these electrons can move to the conduction band. So like this electron can move away from the antimony atom and move around, free to move around. And whereas for the p-type, we have basically extra hole energy levels, so empty energy levels, right? Remember, empty means absence of electron means a hole. So these empty energy levels, right, you can think of it as holes occupying these levels. And so with just a bit of energy, the holes can move down into the valence band. And then the holes can move in the valence band. Right? Because you can think of, let's say, electrons can move freely in the conduction band because it is effectively full of empty states where the electrons can move to. So if hole is the converse, that means holes can move freely in the valence band, right? Where they are full of electrons to move to occupied space, therefore effectively moving the hole. Okay, so yeah, and just one point to note, right, that the y-axis, vertical axis of a band diagram is always electron energy level. So electron moving up takes energy, but remember hole has the opposite charge of electrons. So hole moving down in the electron energy level represents an increase in hole energy. Okay, so moving electrons up takes energy, moving holes down takes energy in the band diagram. Okay, so now let us consider the case of what happens when you put a p-type semiconductor and an n-type semiconductor together. So remember, a p-type semiconductor is one that has excess holes, right? So P stands for positive because positive charge carriers, holes, are present. N-type material is one that has excess electrons, right? N stands for negative because these electrons are negatively charged carriers. And so we have a p-type and an n-type to put together. So p-type is rich in holes, n-type is rich in electrons, right? Correct. So what happens when you have like something rich in something put next to something poor in something? Let's say you have I'm sure you all did the experiment in biology before, right? You fill up a permeable membrane bag with like sugar solution, so that's rich in sugar, and you put it in plain water, pure water, distilled water, right? Where does the water or the sugar move, right? It's down the concentration gradient, correct? So same thing here, right? The hole will move down the concentration gradient from the p-type to the n-type in diffusion, right? This is like your diffusion that you learned last time in secondary school. And likewise, electron will move from the n-type to the p-type via diffusion as well. However, there's a bit difference in this case compared to the case where we deal with like sugar, salt, water, this kind of stuff, right? In that holes and electrons are charged, right? They are charged species. So what happens is that when the electrons move from the n-type to the p-type, right? Let's say your p-type is doped with boron, and let's say your n-type is doped with, I should change the antimony, right? To follow the example below, okay? Doped with antimony. So when your electrons move from the n-type to the p-type, the electrons go to the boron. Remember, the boron already lack an electron, so they will happily take up the electron. And so what we have is that boron ions, B minus, so to speak, right, are now present on the p-type side. Then what happens when holes diffuse to the n-type, right? You kind of think that the n-type also likewise gain a positive charge, right? And what is that positive charge is your antimony plus that has lost the electron. So note that these are fixed charges. So unlike holes and electrons that can move around, these are like ions, they are atoms, right? Atoms in a lattice, right? Atoms in a lattice, can they easily move? They cannot, right? So they are fixed charges. So this charge build-up is fixed. These charges cannot move. So now what we have is that we have built up an electric field. Positive charge on one side, negative charge on one side, electric field arrow pointing from positive to negative charge, right? And so now we have another phenomenon called hole and electron drift. So now holes tends to drift from the positive to the negative side. Electrons can drift from the negative to the positive side. So what is the difference between diffusion and drift? Diffusion is a movement motivated by a concentration gradient. Drift is a movement driven by electric field. Okay, so that's the difference. Okay, and diffusion and drift can, and in fact in this case they do, occur in opposite directions. So there are separate, distinct driving forces behind charge carrier movement. Okay, so let us take a look at some graphs and some maths, right? Even though I said that I'll try to avoid maths, but I'm sorry. This is important enough, I think, for me to cover. So Okay, so we have a P and an N, and remember the N side accumulates positive fixed charges, the P side accumulates negative fixed charges. Okay, so we have your charge density, and so it's positive and negative. And note that this positive and negative charge will cancel out, right? So it's a charge density. So the integral, right, the area under these graphs, right, will be equal, right, for the positive and negative rectangle. Okay, and so what you get when you let me think, integrate, right, charge density is you get electric field. So you integrate a straight line, you get a linear, basically linear relationship, right? Horizontal straight line becomes a linear straight line. Okay, so this represents the electric field in the depletion region over here. So I forgot to mention this region is called the depletion region, right? Why? Because it's depleted of charge carrier. Charge carrier have all diffused away or drifted away, and what is left in the depletion layer are fixed charges. Okay, so fixed charges are left, and so these fixed charges, right, create, as what I mentioned earlier, an electric field that has this geometry within the depletion region. So there is basically a certain maximum electric field that can be computed. And so the integral of electric field, this one you should know. You will get what? Electric potential. Correct? Integral electric field over distance gives you the electric potential. So you get a potential graph like this. So we see a higher potential here and there's a lower potential here. Right? And we do see a graph like that. Okay? Okay. So a few things to take note here would be, firstly, there's this idea of a built-in potential. So as you can see over here, the formation of the electric field results in basically a potential difference between the edge of the depletion region on the N side and the edge of the depletion region from the P side. And so this built-in potential or built-in voltage can be calculated according to this formula. So this formula is pretty important because you see that the higher my dopant concentration, so ND is my dopant concentration in the N region, and my N is the dopant concentration in the P region. So for example, my ND may be a concentration of antimony over here, and my Na will be the concentration of, what was it again, boron, right, in your P region. Okay, so the higher your dopant concentrations, the higher your built-in voltage. Okay, so if you want, like, let's say a large built-in voltage, so you want that sometimes, right, for certain devices, you want a large driving force for electron and hole drift, right? You choose materials that have very high dopant concentration. Okay, and also importantly is the width of the depletion region, right? Is inversely proportional to basically your dopant concentration. Okay, there's this inversely proportional term to be more precise. So the higher your dopant concentration, the smaller your width of the depletion region, right? Why? Because it makes sense. Because if you have, let's say, a higher concentration of antimony over here, you need a smaller region before you have enough antimony fixed charges to build up with sufficient positive charge. Likewise, if you have a lot of boron concentration here, you need only a smaller thickness, a thinner layer, before your fixed charges of boron minus is enough to balance a positive charge. So let me pose this question, right? Let's say if one region is more highly doped than the other, right? The depletion region will be thicker on which end, right? So actually the answer is already here for you. So in this diagram, the P region over here is more heavily doped. And so if you notice, the depletion region is smaller on the P region. Smaller on the P region. Why? Because the P region has more charge, or rather has more higher charge density. So a smaller region of it is sufficient to balance the charges in the N side of the depletion region. Okay, so this is pretty important for certain applications. That this concept is quite important. So another way that you can draw this, right? So note that over here we draw the N having a higher potential, because this potential is defined based on, let's say, a positive charge. Okay, so it's defined based on a positive charge. However, if we define the potential, right, based on, let's say, electrons, the energy of electrons, then we see that the N region, right, becomes lower. The N region becomes lower. And so we can basically draw this by considering, let's say, the band diagram of the P and N type materials as separate, and basically their Fermi levels are over here. So for the P material, the Fermi level is always below the middle, right? Because remember we introduced additional like additional states. Alright, we introduce additional states by adding the dopant atoms, and that alters the Fermi level, right, in the material. Whereas for the N material, right, the Fermi level is above the middle, over here, above the middle. However, when we connect the two materials, right, at equilibrium, Fermi level is always a single horizontal line. It's aligned, correct? So you can accept that, and so in order to be able to achieve the alignment of the Fermi levels, right, in order to be able to achieve equilibrium, in other words, we have to increase the P band and decrease the N band, or lower the N band, until we get the S-shaped, something like this. Okay, and so we get exactly the inverse of this graph over here, but that's simply because of the definition. Okay, so the N side is positively charged, the P side negatively charged. So remember that this is defined based on electrons, so it of course makes sense that electrons are more stable when there's the environment is a positively charged environment, right? So it's lower in energy on this side and higher in energy on the other side. Okay, all right. Wow, okay, so next one, p-n junction behavior. We are not going very fast at this rate, but I guess that's because I want to really explain everything properly. So it turns out that when you connect the P and the N material together to get a p-n junction, it exhibits interesting current carrying characteristic. In fact, it behaves like a diode. Right, you probably heard of a diode before in secondary school. You know that it only conducts electricities in one direction, and the p-n junction functions as a diode, right? I mean, not an ideal diode, right? But effectively, it models a diode can be used to model its behavior. Okay, so in forward bias, right, electrons can or electrons and holes, right? So current can flow through it. Whereas in reverse bias, current cannot flow through it, or basically very little current flows through it. So you can think of it as this way, right? If you apply forward bias to it, you apply a positive potential to the P side over here and negative potential to the N side over here. So remember that when you apply something positive, it lowers electron energy levels because it makes electrons more stable. And when we apply a negative charge, right, or negative potential, it increases the electron energy level. So that's why in forward bias we see that there's the curve becomes more gentle. The curves become more gentle. So this makes it easier for electrons to move from the N to the P side, and holes to move from the P to the N side, because the gradient is not so steep. The gradient is not so steep. Right? However, in reverse bias, the gradient becomes steeper. So imagine if electrons want to follow, let's say, your applied potential, or holes want to follow your applied bias and want to conduct through, right, the depletion layer. However, you observe that there's a much steeper gradient over here, so much larger energy barrier to electron and hole movement. And at the same time, right, what we observe is that the depletion layer grows in thickness, right, because we are applying a potential that basically accentuates this gradient over here, which makes the depletion layer grow in its thickness. And so when you have your layer which is devoid of charge carriers, right, only having fixed charges, when you have it being very thick, right, it impedes current flow through it, right, very little current can flow through it. And so therefore we see that the p-n junction, right, effectively does not conduct electricity in the reverse bias state. Okay, so now let me introduce another concept, which is the metal oxide semiconductor stack. So in this case, you have a metal, you have an oxide, you have a semiconductor. So we sometimes call this a MOS or MIS, where I stands for insulator. So the oxide normally is silicon dioxide, and the semiconductor normally is silicon. Okay, and the silicon dioxide, for your information, is an insulator, electrical insulator. It does not conduct electricity. So basically, we can consider there being three modes of operation. So we normally apply a certain voltage to the metal, and we call that a gate voltage, right? Why do you call that a gate? We'll see later. But let's say we apply a gate voltage. So let's say that the semiconductor or the silicon substrate is a p-type material. So p-type material has plenty of holes, right? Plenty of free mobile positive charge carriers. So we apply a negative, let's say we apply a negative voltage on the gate. So it will attract all these holes to the surface, but it cannot enter the oxide because the oxide is a non-conductor of both electrons and holes, right? It cannot conduct either one of them. So the holes, the positive charge, basically just accumulate at the interface between the oxide and the semiconductor. Okay, so no problem, we can keep on like accumulating these charges because your P substrate is very rich in this positive charge. However, consider the case where you apply a positive gate voltage. Positive gate voltage. So what it does is that it repels the hole away. It repels the holes away. And so what is left behind? What is left behind is negative fixed charges. Okay, negative fixed charges. So they are fixed in position. So this region over here that's in light green now becomes a depletion layer, right? Because there's no more free mobile holes anymore. It's only fixed immobile negative fixed charges, right? So it's a depletion layer, okay, which is unable to conduct electricity, right? The depletion layer is unable to conduct electricity, so it acts also like an insulating layer, right? However, will this continue forever? Right? No, it will not continue forever because when the voltage at the gate is higher than what we call VT or the threshold voltage, right? We can effectively break certain bonds, right, in the P substrate to attract electrons out of the semiconductor. Even though it's a p-type semiconductor, right? It it mainly only has holes as charge carriers. But when you apply sufficient positive gate voltage, you can pull electrons out of the material. And these electrons accumulate at the interface now. And so this is what we call inversion. Why do you call this inversion? Because originally it's a p substrate, it's a hole rich material. But now we have a channel of electrons at the interface, right? Of the opposite charge from what is the norm in a p material, p-type material. So yep, so we call this inversion. So what normally we do is that we take a capacitance voltage curve, uh, profile, right, of this MOS stack, because it can tell you us a lot of information about, let's say, the kind of charges that are in the material, the kind of properties of the semiconductor and all that. And so normally what we see is that this gate and the oxide and the substrate in accumulation mode acts as a single capacitor, right? The oxide is the only dielectric layer, right? It's the only dielectric layer because your P substrate is able to conduct, right? Because it's full of holes that are being attracted by the negative gate voltage. So you should see a constant capacitance under accumulation mode. However, under depletion mode, remember you are growing a depletion layer. The depletion layer is electrically insulating, right? Because there's only fixed charges, no mobile charge carriers. So we can consider the depletion layer to also be a dielectric layer in the capacitor, and it is growing in thickness. And if you remember your capacitance formula, when the thickness increases, capacitance decreases. So you should say a decrease in the capacitance during depletion mode. But what happens at inversion? Inversion, there's a turning point of the capacitance graph at the threshold voltage. And so if we are using a low frequency AC signal to measure the capacitance, right, this AC signal is able to modulate the inversion layer. So effectively what happens is that we return to the original case where the only dielectric is the oxide layer and the capacitance goes back to the original value in the accumulation mode. However, when you're using a high frequency AC signal to measure the capacitance, this AC signal modulates the depletion layer instead. So the depletion layer is still present and is still being modulated by the AC frequency. And so that we, instead of going back up to the original capacitance, it continues, the capacitance plateaus off at this lower value because now the capacitance is still arising from both the oxide layer and the depletion layer. Okay? If you don't really understand this, it's okay for now, I guess. Yeah. So let us take a look at what is a MOSFET device, right? So a MOSFET device. So most transistors that we see in a lot of those kind of integrated circuits is a MOSFET device. So what does MOSFET stand for, right? So MOS, right? MOS is what we saw earlier. metal oxide semiconductor, right? FET, field effect transistor. Okay, so it acts like a transistor. It's not so important that you know, I guess, for this course, the electrical engineering side of things, because I plan to conduct this course as a materials engineering perspective. After all, that is my training. I'm not so familiar also with the electrical engineering side of things, to be very honest. So what we have in a MOSFET device is that basically we have a source, we have a drain, and we have a gate. So where is the MOS? Where is the MOS? Right, the MOS is over here. The gate is the M, right? The gate is usually made of a metal or basically something that's conducting, electrically conducting. The O, the oxide layer, is over here, and the semiconductor is below. So this is what we call N MOSFET. Okay, N MOSFET. N MOSFET is because the channel is an N-type channel, which we'll see later. But basically, what we have is we have a P body, a P-type body. The source and the drain are two small N-type valves, and yeah, we have the gate in the middle. And so what happens is that during operation of an NMOSFET, right, we are sometimes you just call it an NMOS, right? We apply a positive potential on the gate, positive. So what this happens is that this is like the case we saw earlier, right? It pulls electrons out of the P substrate when the gate voltage is greater than the threshold voltage. Okay, so let's say it is indeed greater than the threshold voltage. So what we have is that we have a channel consisting of electrons. So we call this an N-type channel, right? Because it consists of negative charge carriers, electrons. So an N-type channel forms. And what happens? We have an N connected to an N by an N-type bridge. And so this turns on the transistor, and current can flow from the source to the drain. So without the gate voltage, right, current cannot flow, because between the N and the P regions, right, there's a depletion layer. There's a depletion layer which blocks current flow. However, when we form the channel, the N-type channel, it bridges across the source and the drain, allowing current to flow. So this only occurs when the gate voltage exceeds the threshold voltage of the device. So this is what I was talking about. Let's say we apply a gate voltage. So normally call this VGS, because it's between the gate and the source. That's normally how it's defined. So only after the threshold voltage does the drain current, which is the current flowing from source to drain, does it increase. So we can define certain device characteristics, such as the threshold voltage and the transconductance, right, which is defined as like the gradient of the drain current against the gate voltage, right, after the threshold voltage. And so what about, let's say, how the drain current varies when the drain source voltage is varied? So of course, when the gate voltage is below threshold voltage, we observe that there's no drain current, right? So each curve represents a different gate voltage. So of course, when the gate voltage increases, we see that the current increases. So let's take a look at, let's say, one of these curves. We see that as the drain source voltage increases, the drain current increases first in the ohmic region, right? Increases first in the ohmic region, right? Because of course, once the channel is established, the higher your drain source voltage, the more current will flow through the drain, right? However, that does not occur indefinitely. Eventually, we reach a saturation region where further increases in the drain source voltage does not further increase the drain current, right? And so why is the reason for this, right? So this is because of channel pinch off, right? So when your, let's say, source drain voltage increases to a certain point, right, or your drain source voltage increases to a certain point, your drain is, remember, is a positive potential is applied to it. That reaches a point where it cancels out the positive potential applied to the gate at this position. And so we observe that at this position, the gate voltage is insufficient, is below the threshold voltage at this location, right? And so it's not enough to induce a channel at this location. So you can imagine, as the drain source voltage becomes greater and greater, the pinch off location moves further and further to the left. So the channel becomes, right, shorter and shorter. So the channel becomes less and less able to bridge the source and the drain, and the channel will not basically keep increasing in the in its ability to conduct electrons from the source to the drain. Okay, so that's why we observe plateauing in the drain current in the saturation region. So what are certain device characteristics that we tend to look for in the MOSFET? So we want a high on to off current ratio. That means the current in the on mode, that means more than the threshold voltage, right? The gate voltage is more than the threshold voltage, should be much higher, right? Few hundreds or thousands of times higher than the current in the off status, right? The off status. And we also want something called a low subthreshold swing, right? So subthreshold swing is like the amount of voltage needed to introduce an increase in the current at the subthreshold region. Right, so we want it to be lower so that it's better able to introduce the turning on of the device. We also want a low channel resistance when the device is on, so that there's not too much joule heating and not too much like basically resistance that reduces the current as well. And we also want low leakage current, so we'll maybe go more into this maybe later on when we talk more about the device itself and fabrication considerations. But basically, leakage current can occur in various ways, right? There are various types of leakage current, right? There can be subthreshold leakage, right? That means conduction of current, right? Below the threshold voltage, right, which is not desirable. They can be punched through, right? Punched through current. There can also be leakage, right, through the junction, right, into the body of the device, right? And so we want to decrease these leakage current values as much as possible. Okay, so this marks the end of this particular video. So in the next video, I will have an overview of the fabrication workflow for a CMOS device, which is basically something that I introduced in the next lecture. And I'll also cover things like trends in the MOSFET design. Okay, so this is the end of this video. Thank you.